Thanks for coming. My name is Masoud Agah. I am from the Electrical and Computer Engineering Department, Virginia Tech, and I'm presenting this on behalf of the students working on this project, Wang and Muhammad Akbar, and my collaborator in the physics department, Dr. Randy Heflin. So this project falls in the micro-analytical chemistry research trust in my lab. There are 3 research trusts that we are basically pursuing, and through the IEEE Sensors Conference, we have presentations, at least one per one of these research areas that you can also come and listen in the following days. So in the microanalytical chemistry trust, we are mainly working to develop a miniaturized gas chromatography system. So what is basically gas chromatography or GC system? So it's a system based on the separation principle. So what it does is that it separates the components of a gas mixture into individual compounds, and then it can detect them. So when it comes to environmental monitoring or for a portable system, then there are essential elements in this micro GC or GC systems. One is what we call a preconcentration stage. That basically is the one that traps the compounds. The second stage is the heart of the system where the separation happens, and that is called separation column. And the third element is the detector. So what is the function of the preconcentration? The preconcentration basically acts as a chemical amplifier. In the environments when you have a low concentration of the analytes in the environment, so what you need to do is that you need to enhance the concentration. So if you have low concentration, what happens is that your detector cannot detect the components because it will be below the limit of detection of your detectors. So what you can do is that you can put a trap, and then these compounds, as they pass through this trap, they're getting trapped, obviously, yes? And then you give them enough energy by hitting it up, and all these adsorb components, then they get desorbed and they go to the detector. And now you can have a very concentrated plug that sends your signal above the limit of detection of your detector. When it comes to the separation column, this is basically a channel or a capillary tube in this example. And this tube basically is coated with a polymer which is called a stationary phase. So the sample is forced through this column by a mobile phase, which is an inert gas such as helium or nitrogen. So the gas which is mixed, then it goes through this, interacts differently with the stationary phase, and at the end it can get separated over time and a space, and it can pass over a detector, and then a chromogram is being generated. So the retention time, or the time that the compounds spend in this separation column, can be used to determine which compound is present in the sample. In the lab, basically, we work on all these different elements of a micro GC. We work on the micro-fabricated preconcentrators, and this presentation is about this one. I think Wednesday and tomorrow I will talk about the efforts that we have on the separation columns and also integration of the separation columns with thermal conductivity detectors. So but what about the micro preconcentrator? Let's talk about that one, which is the focus of this research, so of this presentation. So in the past several years, I think 5-6 years, we have been pursuing the development of these chips, which are basically having cavities with thousands of embedded pillars, thanks to the efforts of my former graduate student, Dr. Asili, who's sitting here. So these are basically some of the different structures that you see here. I mean, we did a lot of investigations on the effect of the pillar geometry, on the effect of the flow distribution. For example, if you look at this one, you see that we distribute the flow, and we have shown that can enhance the interaction of the gases with these pillars, and we can also enhance the concentration efficiency. So what happens is that when you go ahead and do this, what happens is that you create a chip which has a very large surface to volume ratio, which is essential for having an effective gas adsorption. So what happens here is that these pillars basically are coated with a polymer. So the gas comes in, and it interacts with these polymers, and it is being adsorbed on the surface of these polymers. So if some of them escape, then you can generate a breakthrough peak. So ideally, we want that breakthrough peak to be 0 during the adsorption phase. If you have a large breakthrough peak, it means that your adsorption has not been pretty effective. And then what you do is that after you have collected enough sample over a period of time, then you go ahead and heat it up. And then you can dissolve all these species. And as I said, it goes through the next stage, which can be a separation column or detector. So again, ideally, we want to have large surface area so that we can collect all the analytes. And at the same time, since we are heating up this structure and as a result, the polymer, we want to have good thermal stability of the adsorbent bed. We don't want it to degrade over several thermal cycling stages. And at the same time, we want it to be stable at very high temperatures, because in the environment, we might also be interested not only in the extraction of volatile organic compounds, but also semi-volatile organic compounds, which means that we need to go to much higher desorption temperatures. So what we have been using in the past several years, we have been using different polymers, including Tenax TA, which is widely used, again, for gas adsorption. We have done some work on PDMS, which is not as effective and as thermally stable as Tenax TA. And we have also worked with DVB particles, and we have utilized them for breath analysis applications. So when it comes to Tenax TA, which is again widely used also for microtraps, which are the commercial preconcentrators, we have shown that we can convert them from the particle form. The company basically sells them in particles, which is not compatible with this technique that we want to use. So what we have done in the past several years, we have been able to convert them into thin films. We have been able to use, for example, inkjet printing for the first time to deposit them on these as pillar structures. And we have been able to develop various techniques to create nanorod Tenax TA for enhancing the adsorption capacity, or we create very porous films, again, if we deposit at high temperatures. So this polymer has been pretty good, actually, in adsorption. However, there is still a problem. One is that the deposition conditions can affect significantly the film properties. And sometimes, even under same conditions, you might get different film properties. That shows that the repeatability can be affected by the method. The other thing is that the film thickness is not, the film thickness that we deposit is not well controlled. I mean, we have some control over it by the initial concentration of the Tenax in the solution, but it is not pretty well controlled. So we're looking for alternative methods that can also be used when we have a very packed structures inside the cavity. So we thought, okay, why not going after nanotechnology? That's a hot topic, yes? So let's think about nanotechnology and see whether we can utilize that. So we started thinking about that one. Initially, we started looking in gold nanoparticles, and then we moved into silica nanoparticles. We investigated them as an adsorbent material and wanted to see whether we can really use them for gas adsorption or not, and whether we can really create a good coverage on these pillars, create a porous structure, and also do 3D patterning, which is essential for this type of micro-fabricated preconcentrators. So we went after this fabrication process. So the first thing that we do is that, as you see here, we do deep reactive ion etching. So we do deep reactive ion etching, we create the pillars, and we etch silica. This is the key point, without stripping the photoresist, we go ahead and utilize layer by layer assembly. This is a very straightforward technique that relies on the electrostatic attraction between positively charged materials and negatively charged materials. So the positively charged material in this case is PAH. Negatively charged material is silica nanoparticles. So we dip it in PAH and for a few minutes, then we dip it in silica nanoparticles. We can do a washing station in between, or we can go ahead again into PAH, into silica nanoparticles. So we can repeat this, and then we can really control within nanometer resolution the number of bilayers that we can put on this surface. We can put 5 bilayers, 10 bilayers, whatever we want. I mean, this is very well controlled. I mean, the thickness can be controlled to the extent that we want. So if you remember, I said that the key is that we don't want to remove the photoresist. Why? Because silicon nanoparticles will sit on the top as well. So what we did here again for the first time is that we wanted to do selective patterning of these nanoparticles so that we can have it only on the sidewalls and at the bottom. We want the top surface of the silicon to be clean so that we can do anodic bonding. So what we did is that we said, okay, why not using lift-off technique, which is being used in semiconductor processing and MEMS fabrication for metal deposition. So what we did is that, again, we put it in acetone and we sonicated it, and we noticed that we can really create a very clear surface at the top. And what we have here are the silicon nanoparticles just on the sidewalls and the bottom. The top surface is clear, and we can go ahead and do anodic bonding of a Pyrus wafer to the silicon structure and seal the structure. We can also do calcination, which means taking it to the high temperature, 500, 600 degrees C, so that we can decompose the polymer and diffuse the silicon nanoparticles into each other to make it pretty much stable, and we can take it to very high temperatures after that. So these are SEM images of the silicon nanoparticles deposited on the sidewalls or also at the bottom of these structures. So you can see it is pretty dense, pretty conformal. And these are, again, we have plenty SEM images that you see here. So in terms of the separation or the characterization conditions, we use commercial gas chromatography systems. As you see here, if we don't have, on our structure, if we don't have any nanoparticle, it is just silicon, we get a very large breakthrough peak, which means that silicon by itself cannot adsorb anything. So when we go ahead and put these silicon nanoparticles, then we are able to adsorb xylene, and no desorption peak is no breakthrough peak is observed. So we go to adsorption, and then we increase the temperature, and we go to the desorption stage. And this one shows the successful adsorption of 3 compounds in a gas mixture, so toluene, chlorobenzene, and xylene. And then we use a separation column after that to separate it. So it shows that this nanotechnology can be really used and merged with the MEMS technology to develop micro-fabricated preconcentrators for the application of micro. So that's all, and I want to also acknowledge the funding which was provided by the National Science Foundation. So I would be happy to answer any question you want. Thank you. Good. An answer. So. You have used silicon dioxide nanoparticles. Silicon nanoparticles. It's all your 2 nanoparticles. Yes. And what about the agglomeration of them? Because I think they are below 200 nanometers, and especially when they are in below 50 nanometers, the agglomeration occurs, and this cannot be prevented in the system. So that's a very good question. Actually, the reason we abandoned gold nanoparticles was that we observed this agglomeration in gold nanoparticles. You know, so that one we observed in gold nanoparticles. Maybe they're softer, I don't know whether, but they can migrate much easier. With silicon nanoparticles, we didn't notice that. I mean, I have plenty of different SEM images that I can show you. Even on silicon surface, we deposit them, and then we take them to very high temperatures. We do calcination, and they're still okay. We don't see that agglomeration. But that one we have seen in gold nanoparticles, and that's why we didn't continue using gold nanoparticles for this particular application. Again, for sensor applications, it might be great, but not for this application. This one, we can really take it even to Tenax. We have shown we can take it to 400 degrees C. This one, we can take it to 500, 600 degrees C. So any semi-volatile compounds that absorb on it, they can be dissolved. So. Mm. Yes. So the porosity to some extent also comes from, so as far as we have a molar and then we can have the second one, that for us creates the porosity that we need. Yes, the other thing you need to know is that we don't want to, there's a trade-off. At the other hand, you don't want to create a very porous surface. Why? Because then the gases goes in, then it becomes very difficult to escape. So this one, again, there are a lot of characterization we need to do. I mean, the size of the nanoparticles, the number of bilayers that you want to put on it. So those are all the things, and also the affinity with the different components. Those are still things that are under development and research. So we're working on it. Thank you.